So far, we have dealt with changing magnetic field and discussed Faraday's law that said that a changing magnetic field produced an electric field, and this relationship was given by this. So, there is a counterpart of this is that changing electric field also gives a magnetic field, and this term is known as the displacement current, and this is going to be our topic of discussion in this lecture. And from now on, we are really getting into electrodynamics that involves changing electric and magnetic fields. Along the way, we will now understand what quasi-static approximation is, and then go on to discuss Maxwell's equations in their full glory. So, let us start with the discussion of displacement current in this lecture. So, 4 Maxwell's equations before displacement current was introduced are: divergence of E is 0, or even better, rho upon epsilon 0 in presence of charges. So, I am going to erase this. Then curl of E is minus dB by dt, divergence of B is 0, and curl of B is mu 0 j. This is all fine, except now there is a mathematical problem. The divergence of curl is identically 0 for all vector fields. Now, let us look at this equation. Curl of E equals minus dB by dt, and take divergence, which gives me divergence of curl of E is equal to minus d by dt. I can take divergence n. The left hand side is 0, divergence of B is 0. So, this is fine. Let us look at the other curl equation. The other curl equation is curl of B equals mu naught j. So, divergence of curl of B is mu naught divergence of j, and this is identically 0. On the other hand, for time dependent systems, this will come out to be mu 0 d rho by dt with a minus sign. This is bicontinuity equation. Divergence of j plus d rho dt is 0. So, left hand side is 0 and right hand side is not, and therefore, I have to correct the equation. So, we have divergence of curl of B equals minus mu 0 d rho by dt. This is 0. So, must add another vector to the right hand side. So, let us write curl of B is equal to mu naught j plus another vector, let us say V. And what we should have is, if I take the divergence, 0 equals mu naught divergence of j plus divergence of V, and this is minus mu naught d rho by dt plus divergence of V. So, divergence of V is going to be equal to minus mu 0 d rho by dt. And I know that rho is equal to epsilon 0 divergence of E. Therefore, d rho by dt is equal to epsilon 0 divergence of dE dt, and this gives me mu 0 d rho by dt, where the minus sign should be equal to minus epsilon 0 divergence of dE dt. I should make a correction here. This should be plus. Now, this immediately implies that V equals epsilon 0 dE dt. So, this is known as Maxwell's displacement current. I should actually have curl of B is equal to mu 0 J. There is a mu 0 sitting here plus mu 0 epsilon 0 dE dt, and this term epsilon 0 dE dt is known as the displacement current. Displacement, because epsilon 0 E is related to displacement in a dielectric medium. So, we will call it displacement current. It has obviously dimensions of J, right. So, our 4 Maxwell's equations now are divergence of E is equal to rho over epsilon 0, curl of E is minus dV by dt, divergence of B is equal to 0, and curl of B equals mu 0 J plus mu 0 epsilon 0 dE by dt. So, what it means is that changing electric field can also give rise to a magnetic field, just like changing magnetic field gives an electric field. I would like you to pause a little here and imagine in this that you have this fields, and if you have a changing magnetic field, it gives rise to an electric field, and since B is time dependent, E will also be time dependent, and this changing electric field gives rise to B. So, there is this lot of interplay going on between the two. Let me ask you a question here. If there was no free current, that is J is equal to 0, what will be the solution for magnetic field due to dE dt? And again, you have to be careful, this will be in the quasi-static approximation, which I will talk about a little more in this lecture, so that you understand it fully. So, we have looked at how this term displacement current arises from mathematical point of view, and this is related to charge conservation through the continuity equation. Let us now look at it from a physics perspective. Obviously, it will involve some mathematics. So, let us look at a capacitor, simplest parallel plate capacitor, in which there is a current I is coming in and I is going out, so that there is a charge accumulation here. q is a function of t, such that dq dt is equal to I. Let us now think of magnetic field existing all around, right? And what we do now is take a loop for the magnetic field. There is a current coming in, and I will take a loop here in which the magnetic field exists, and here is the direction of the loop. If I look at this area of the loop, then current I is passing through it. So, there is this current I which is passing through it. If I take B dot dl across this loop, this is going to be mu naught I, which is not equal to 0. I can also do one more thing in this, and that is I can make this loop and enclose it from behind. This is the balloon like area. In that case also, if I take B dot dl, since there is no current going through this balloon like surface, this will come out to be 0. So, you get 0 through one loop and non-zero through other loop. There must be something wrong in the equation. So, we correct the equation by including displacement current, and I will leave the rest for you to do. So, here is a physical perspective. You look at it and you will never forget it. Now, let us play with these equations a little more. So, we have these 4 equations. Divergence of E equals rho over epsilon 0, curl of E equals minus dB dt, divergence of B is 0, curl of B equals mu 0 j plus mu 0 epsilon 0 dE dt. Let us look at these equations when no free charges and no free currents exist. In that case, the equations are, then we have divergence of E is equal to 0, curl of E equals minus dB dt, divergence of B is equal to 0, and curl of B equals mu 0 epsilon 0 dE dt. You may ask, if there are no free charges or free currents, how do these fields arise? So, then these equations are to be solved with proper boundary conditions, right. Just like if I have the Laplace's equation del square phi equals 0, it does not mean that phi is 0, because there is some boundary condition. Similarly, E and B will exist with some boundary condition. At boundaries, the fields exist because of some sources. So, now let us go further and take the curl of one of the equations. So, let us take the curl of the curl equation, curl of E equation, and this gives me minus d by dt of curl of B. The left hand side by vector identity is divergence of gradient of divergence of E minus del square E, and the right hand side is minus d by dt of mu 0 epsilon 0 dE dt. Divergence of E is 0, and therefore, I get the equation that Laplacian of E minus mu 0 epsilon 0 d 2 E by dt square is equal to 0. It is like the wave equation for E. So, E propagates like a wave. Similarly, if I take curl of B, this will be mu 0 epsilon 0 d by dt of curl of E, and this also gives del square B minus mu 0 epsilon 0 d 2 B over dt square is equal to 0. So, these are wave equations, and the solutions will propagate like waves. So, from Maxwell's equations with rho equals 0 and j equals 0, we get wave equation for B and E. The most general solution is that E as a function of r and t will be some function, right, some g of r plus c t in some direction of propagation plus some f r minus c t in the opposite direction. Let me erase this vector from the top. And similarly, I can write B also would be similar. G, not necessarily the same function, C t in some direction n plus some f r minus c t in some direction, in the opposite direction. So, these are directions of propagation, these are the most general solution, the solution of the wave equation. And this means any E or B arising from changing fields, and that means what means is dE dt not equal to 0 and dB dt not equal to 0 travels with speed c, c being 1 over square root of mu 0 epsilon 0, which is speed of light. This much you know, but having built this up, what I want to now understand fully from this is what is quasi-static approximation then, right. So, in general what will happen, I make this E change with time, B change with time, it generates fields, and that field propagates with the speed of light, and then we are done. But I have also been talking about quasi-static approximation when we discuss Faraday's law. Now, we have one more time dependent situation, and I want to understand what this means. So, let us do that. So, imagine this, there is some source somewhere, right. This may have some rho which is a function of r and t, this may have a j which is a function of r and t. So, both the charge density and j are time dependent. Since I said sourceless, let us look at the boundary. So, here is the source which I am isolating, and at the boundary, let me make the boundary outside, I have these B and E changing, right. So, here are E and B changing. Let us look at some B which is a function of time at the boundary, and this creates an electric field. So, I have, let us say, B 1 t at the boundary. It gives me an electric field E 1 t generated right there, and this propagates with C. And as this E 1 propagates, this means in the regions where it is propagating, del E 1 by del t is not equal to 0. So, I have a changing electric field. So, this changing electric field d E 1 d t gives rise to additional magnetic field B 2 t. And then there is this B 2, which could be like this. This is also propagating with C. So, B 2 would then give rise to E 2 and so on. So, what do I have starting from the boundary? I have B 1 t giving rise to E 1 t, or let me write the E the way I have been writing, and E 1 t giving rise to B 2 t and so on. Net field at any point is the sum B 1 t plus B 2 t plus so on, whatever it comes from the boundary condition, and similarly E field would be E 1 t plus E 2 t plus so on. What quasi-static approximation involves is that I ignore the higher order. That means they have to be really small compared to what we started with. And then the quasi-static approximation would be valid. So, let us see, what did I do? I have a source which is producing a field at the boundary, and then things are propagating from here onwards. I have a B 1 t gives rise to E 1 t. So, I would have curl of E 1 equals minus d B 1 over d t. And as E 1 changes, I would also have curl of B 2 is equal to minus d E 1 d t. And I want to understand when can I ignore B 2 magnitude in comparison to B 1. So, let us now quickly do some calculation. So, here is the boundary, here is some B 1 t giving rise to E 1, right. So, let us say I am calculating E at some distance, it will be coming out because of the curl equation. So, this is E 1, and let us say this distance is L, and the time scale for change is of the order of tau. For example, if B 1 is cosine omega t, then tau would be of the order of 1 over omega. So, here is this source, here is this initial B 1, here is this E 1, then I have E 1, curl of E 1 is minus d B 1 by d t. Curl of E 1 I can write as E 1 magnitude by L from the magnitude point of view, because L is over which it will change. And this is of the order of B 1 over tau. So, I have mod E 1 of the order of L over tau B 1. Similarly, now I can go to B 2. I have curl of B 2 equals minus, oh, this equation was wrong, this was mu 0 epsilon 0 d E 1 by d t. So, this is mu 0 epsilon 0 d E 1 by d t. So, again if I go back to this picture, here is my B 1, there is some E 1 existing all over, and this E 1 gives rise to some additional field, let us say B 2. So, B 2 again, because the time scale would be mod B 2 over L, the curl equation will give you that, is of the order of 1 over c square mod E 1 over tau. And if I put the value of E 1, which is B 1 by tau times L, so this gives B 2 is of the order of L square over c square tau square B 1. In the same manner, you can argue for E 2. You can show that E 2 is of the order of L square over c square tau square E 1. If second order is to be ignored, then L over c tau better be much less than 1. So, this is the quasi-static limit, is the limit in which quasi-static approximation is good. If you go to the other limit, in the other limit, B 1 by itself, it just may die down, and L over c t tau would be much greater than 1, and in this case we get self sustaining fields. So, here is a source or a boundary, right. Let me make the boundary thicker. Then close by in some region where L over c tau is much less than 1, I can apply quasi-static approximation or Biot-Savart law or whatever. And then when you go far away, really far away in these regions, self sustaining field. That means E and B changing and they are sustaining each other. So, here in the inner region, let me now write it, shade it, I can apply Biot-Savart law like formula for calculating B and E. I have already asked you a question, what will be the formula for B under quasi-static approximation when B is produced by dE dt. I will solve a couple of problems in the next lecture, and then you will see it more clearly. So, to conclude, I introduced displacement current, and that completed a set of Maxwell's equations, then I obtained the wave equation for E and B in charge and current free regions, and finally understood what quasi-static approximation means. Thank you.